Welcome back. We will continue our discussion on soft lithography. We already have discussed about some of the techniques which include capillary force lithography, micromolding in capillaries, solvent assisted micromolding and some such methods. The common thing about all the methods we have discussed so far had been the fact that all these methods are successful in generating topographically patterned surface. Now, right at the beginning of this course, we have defined or discussed what is the difference between a topographically patterned surface and a chemically patterned surface. So, topographic pattern essentially there is a physical contour along the surface or on the surface. It is let us say it can be something like this, like a grating at the simplest form or more complex patterns. Now, the knowledge we have acquired so far, we understand that it is possible by almost all the methods we have talked, the soft lithography group of techniques as well as methods like nano imprint lithography to generate a perfect negative replica of a stamp pattern. So, if you want to make complex patterns, let us say array of square pillars or circular pillars or something like this, eventually all you need to have. So, maybe this can be a 2D array of cylindrical protrusions. So, what is necessary is that you have the appropriate or the desired stamp, which of course contains the negative replica of the final patterns you want to generate. However, we have also talked about the fact that soft lithography to some extent is limited by the availability of the appropriate type of stamp, which in most cases has to be made by some other lithographic technique, which can be photolithography or any one of the direct write methods. Okay, so, these are some of the limitations of soft lithography, and in the previous class we also discussed the so called concept which is now becoming very popular, the concept of beyond the master patterning. Master eventually here means the mold or the stamp available to you, which is lithographically fabricated. And the ideas are very simple. So, let us say you have one stamp with simple grating, but you try to generate structures which are no longer limited to a perfect negative replica. You can generate more complex patterns, you can play around with the dimension, geometry, line width, height, whatever. So, what it makes is that this really makes soft lithography a method which can be implemented and executed by non-experts. Non-experts here I mean people who do not have significant lithography facility, because at heart if you look, majority of the soft lithography methods are very simple to execute, but often what happens is you still are stuck up with certain requirements, hardware requirements like the stamp or whatever. So, those are some of the things we discussed. Today we are going to talk quickly about 2-3 more methods for generating topographic patterns, all of which essentially make a perfect negative replica of a stamp, but they are easy to execute, but in certain cases they work with some specialized class of polymers or require some specialized type of stamps. And then we move on to 2 interesting aspects. One of them is we talk about microtransfer molding. We have already talked about this method briefly in one of our previous classes, and eventually we talk about microcontact printing. Though the methods sort of sound quite similar, there is somewhat significant difference in the final products or what they finally make, and both are unique as compared to the other methods because of the fact that microcontact printing is probably the mainstay of making a chemically patterned surface. Majority of structures which or methods which make chemical patterns, essentially if you remember, we have talked about what chemical patterns is. So, you do not have a topographic feature, but let us say you have a surface and you have different wettability regimes or regions on the surface. Okay. So, let us say these green patches correspond to zones which have surface energy, let us say of gamma 1 as compared to a background surface energy gamma 2 of the surface. So, this is a chemically patterned surface, and the only method by which you can make such a surface is microcontact printing. Now, microtransfer molding is also rather unique in the sense that this is the only method that allows you to fabricate 3D structures. Well, this is interesting because of the fact that soft lithography or any other lithography technique we have talked about, they are all essentially surface patterning techniques, and they are therefore their output or the patterns you generate to a large extent are limited to the two-dimensional world. Okay, but it was also realized that it would be really good if some of these methods can be extended for fabricating 3D structures, and that is precisely what with some limitation of course, microtransfer molding has sort of allowed us to fabricate. Okay. So, these are some of the methods we will be talking today. So, the first method we talk is essentially this goes by the name step and flash imprint lithography or SFIL. It is something very similar to it is a combination of imprinting and molding, I would say. So, all what is done is that you take a substrate, you dispense a liquid polymer. Okay. So, this is in a liquid state. So, viscosity is very, very low, and then you bring in a stamp or a mold, and simply place it over it or apply a low pressure. So, what happens is you achieve mold filling rather easily. Okay. So, this you have achieved, and this is, please remember, this is in a liquid form. So, the only problem is that you have to somehow solidify it, otherwise it is of no use, because what is going to happen the moment you are going to withdraw the mold, it is going to flatten out. So, once you are in this configuration, what is done in this method is that you do an UV exposure, and this UV exposure leads to an polymerization or cross linking I would add the word pre-polymer here. Of the polymer. So, this is a very simple method, very fast also. That is another big advantage of SFIL, that it's extremely fast. Pretty rapid. Unlike NIL no high pressure requirement is there. No pre-processing in the form of no heating, solvent vapor exposure required, like capillary force lithography. So, you do not require that, you do not require high pressure, you do not require very long time like mimic. The biggest advantage is that you take a pre-polymer which is at a freely flowing liquid condition. So, it is a low viscosity liquid pre-polymer, and therefore, once you bring in the mold on top of it, maybe you just put an apply liquid, a little amount of external pressure, maybe you do not put in any pressure. What happens is the pattern replication is instantaneous. This is the biggest advantage. But what are the limitations? There are a couple of material limitations that comes in with SFIL, which makes the method a little bit of specialized. There are actually, if you have followed the flow sheet carefully, you would immediately realize that there are two specific material requirements and one additional hardware requirement in comparison to something like capillary force lithography, which is even more simple, which is not confined or which is not restricted by the requirement of these additional things. So, what are those requirements? If you just care to think it over for a minute, the first requirement is that you need a pre-polymer which is UV curable. Okay. So, any liquid pre-polymer will not work, because the way the method has been designed, it is essential that your pre-polymer is UV curable. The second requirement is the mold or the stamp. This has to be transparent to UV light. Okay. So, if you just take a stamp, let us say which is opaque to UV, then what is happen that your UV exposure will not reach the film, will not reach the patterned pre-polymer, patterned liquid pre-polymer film. So, it will not harden or it will not cross link, and therefore, the method will work, you will get in situ patterns by placing the stamp, but you will fail to convert them into permanent structures. So, this is the second requirement. The third requirement is, of course, you need to have an UV exposure system. Okay. So, these are the additional requirements of SFIL for perfect implementation or proper implementation of SFIL. However, still this method has quite a few advantages. So, if you have these facilities and if you have the desired type of polymer, it's the easiest thing is that it's extremely fast and rapid, and since the mold filling is in liquid state, and is with a low viscosity polymer, low viscosity pre-polymer, I would repeat. So, pattern replication is excellent. It is excellent actually, because one has to understand that if you compare this with capillary force lithography, you are actually achieving the pattern replication with a polymer. So, you have capillary rise. So, I will just revert back to CFL for a minute. You have the desired capillary rise, but the capillary rise is of a material which is in a liquid form, but it is a polymer. So, it has long chain molecules, the molecular weight is high, and high molecular weight would invariably lead to higher viscosity. So, the dynamics will be inherently slow. In contrast, you here in SFIL you are working with a pre-polymer. So, the material has not yet polymerized, the chains have not cross-linked, they are sort of free flowing liquid like, and in many cases the polymers you work with for SFIL, they are more in a state like simple water. So, all you do is the moment you place the stamp on top of this pre-polymer layer, you immediately have a sort of a pattern replication taking place, and you get so very fast replication, as well as the key important thing is the fidelity of the structures is very, very good. So, this is in a nutshell your SFIL. Of course, you must understand that SFIL would be leaving behind structures with a remnant layer, because you had dispensed a liquid like this. So, you have a polymer both over the valleys and the protrusions of the patterned layer. So, the final structure contains remnant layer, and therefore, these have to be removed by some etching technique. Dry etching, or reactive ion etching. So, eventually that way with combination of etching you can get freestanding polymer structures, and also compared to these patterns your aspect ratio of the structures will also go up. The second method I would like to talk about is what is known as the solvent assisted polymer bonding lithography. This is a simple method. All you do is that you take a stamp and you coat it with a layer of polymer. So, this is your stamp or the mold, and this is, let us say, your substrate. So, this we are discussing here. So, this is your substrate, which can be any standard rigid substrate like a silicon wafer or glass or quartz or whatever. This is your stamp, and you can work with a PDMA stamp here again, unlike in SFIL where you require a specialized UV transparent stamp. So, so all we do here is we coat the substrate as well as the stamp with a layer of polymer. And in the previous class we have talked that when you try to coat a patterned substrate or a topographically patterned substrate with a liquid by spin coating, what happens? So, you might get discontinuous structures, you might get continuous structures with undulating top surface, or you can get a continuous structure with a flat surface. The key being that if your structure, if this height of your liquid layer is significantly larger than the feature height, then it becomes flat. So, what you have, you start off with a layer of polymer, and which is coated both on the stamp and substrate. Important thing to remember that coating on stamp, this will work with both undulating and flat surface of the coated polymer layer. We are talking about, let me just remind, we are talking about this layer. Please refer to previous day's class, lecture number 20 on soft lithography, or soft lithography lecture number 5, where we talked what can be the likely consequences or morphologies if you coat a directly coat a polymer layer on a topographically structured surface. And let me remind that this method works for either this layer to be perfectly flat or even if it is undulating. The key requirement is that the layer has to be continuous. With the first situation where we talked that the concentration is too low and you have isolated structures, then it of course does not work. And once you have these layers coated, all you do is you bring the two in contact. So, this is your stamp now, this is your substrate, and you simply bring them in contact. So, this is where the interface lies. So, this part of the polymer was coated on the substrate, this part was coated on the film, and once you bring them in contact, you can do several things. You can press them hard, you can heat them up. If it is a linear chain polymer, what will happen that by heating beyond Tg, it will be in a liquid like form. So, eventually what will happen is this interface will disappear, interface between the two polymer layers, one coated on the substrate and one coated on the stamp. So, interface disappears, and what you will be left with is a single layer of polymer. And a single layer of polymer, which is now this big the simple cohesive bonding or cohesive attachment. So, this is where let us say you had the interface, and let us say you have heated it up beyond the glass transition temperature, and so it is all liquid, and it is now a single monolith or a single block of the polymer. So, the easy thing to do would be to cool it down again to room temperature, so that the whole mass now solidifies, and then just remove the stamp. Which can be achieved by let us say something like swelling or something like that, and then if you remove the stamp, you have the substrate and you are left with the polymer layer. Okay. So, this is what is solvent assisted polymer bonding lithography, and it is one of the simplest methods, very easy to execute, not material specific at all, and you virtually require no hardware other than the stamp. There is another, so some extension of these methods can be a nice work. I just thought that I will show it, is imprinting or replicating. It is very close to all the concepts of SFIL or simple imprinting also. Imprinting on a hydrogel. And we talked in the previous class, we gave some examples of patterning beyond the master. So, this is another example of that. Now, while introducing to you soft lithography, we did talk that soft lithography works very well for different types of materials like not only polymers, but gels, inorganic sol gels, etc. So, you can just check out this hydrogel. This is a soft swollen polymer network which contains a lot of water. So, if you remove the water in a controlled fashion, you observe a significant amount of shrinkage of this hydrogel layer. So, in this particular method, what was done is that so soft lithography has been pretty routinely used for patterning hydrogels, not a great deal, but typically people have used soft lithography to pattern a thin layer of hydrogel. Okay. So, this is let us say the substrate, and this is the hydrogel layer, and by any of the soft lithography techniques you can very easily get a negative replica of the stamp. In this particular method, what was done, that instead of a thin layer, a block of hydrogel was patterned, a self standing block. It is a simple replica molding, you can say. Hydrogel is liquid like at room temperature, you sort of place the stamp and you get a negative replica. And then you, so what was done, so after this layer was patterned, it was now allowed to shrink with evaporation of water. Now, the moment water starts shrinking, there is significant volume reduction, which can be of the order of 60, 70 or even 90% depending on the initial water content. Now, the idea was, as this block of hydrogel shrunk, the surface features present on the surface of the gel block also shrunk. So, you started off with something like this, you do a controlled evaporation and you get to a block size like this. So, what is the advantage? You had started off let us say with a feature dimension of let us say lambda 1, height of h1 or line width of LP1 let us say, and because of this shrinkage you have now reduced to lambda 2, LP2 and H2, each one of them is smaller than the dimension of the original master. Now, not only this, what was subsequently done was this pattern on the hydrogel surface was reproduced, or this was now replicated on a PDMS block. So, you now have a negative replica of this structure on a PDMS block, which now becomes the second generation stamp. So, you had a PDMS block which contained the negative replica of this structure, which was the, so this is a PDMS stamp, generation 1 stamp. You imprint with that a block of hydrogel, you shrink it. This shrunk hydrogel layer now is the structure on top of that is replicated on another PDMS block. So, that becomes a second generation stamp, and you just continue the same process. So, now you use this second generation stamp to pattern another block of hydrogel, again achieve controlled shrinkage or evaporation, and then you can get to even smaller feature size. So, you see here that starting off with a layer which is let us say a periodicity of 1.5 micron, in the second generation you achieve roughly 40% shrinkage. So, the periodicity has now dropped to about a micron. You can measure that. Here you have 8 micron and you almost have 8 stripes. Here you had roughly 6, and this now, so this is now the second generation stamp. You re-imprint another block of hydrogel with this one to get a third generation stamp which has even smaller feature height. So, this is a very unique concept where a combination of imprinting plus shrinkage has been sort of used to achieve patterns which are smaller in feature dimension as compared to the original stamp size. Now, this brings us now to microtransfer molding, which is, as I have already pointed out, slightly unique in the fact that this is a method by which you can make 3-dimensional structures. So, it is again very simple to execute. All you do is you initially take a PDMS stamp, and coat it or dispense a liquid pre-polymer. We have already talked about pre-polymer in case of SFIL. So, it is not fully polymerized. You dispense a pre-polymer, and then what you do, you sort of scrape it off from the top. So, you are left with a structure like this. So, your molds are filled up with your pre-polymer, and then you do an in situ polymerization. So, scrape off, do an in situ polymerization, and then what you do, you just turn it, somehow swell this stamp. This PDMS stamp can be easily swelled by exposure to chloroform vapor, it swells. So, this way if you turn it down, so what happens is, if this is let us say a grating structure, so these are individual sort of strips of this polymer. So, you turn it down, keep it on a substrate. So, here is a substrate, here you bring in the this is now contains the polymerized strips. This is now turned here. So, now you what you do is you swell the stamp so that it detaches and withdraw the stamp. You leave behind isolated strips of the material on the substrate. Now, so this is fine, you have some nice strips like this, but what is the advantage? Advantage is that you can repeat this process again. Okay? You can take another stamp, scrape off, fill it up with the dispensed polymer, scrape it off, do the polymerization there, and now suppose you bring in that stamp and place it over here, swell it. So, in the process now you can place this new sets of strips like this. So, you have, let us say, these strips over here, okay, and so this way you can go on building in a way layer by layer and go on adding different layers. So, again the third layer can come in like this. So, this sort of gives you the ability to create true 3D structures. The examples I picked up for ease of understanding is of course limited to the fact that you have taken a grating stamp, but you can start off with a more complex stamp and can have hierarchical features or other type of features by microtransfer molding. But this is please remember, this is probably the only soft lithography method that allows you to fabricate structures which are with full or true 3D capability. That brings us to microcontact printing eventually. So, let us have a quick look at the classification again. What are the things we have discussed? So, we have already discussed the NIL group of methods. So, the imprinting group of techniques with rigid stamp or mold. And then we have significantly discussed the soft lithography group of methods which use a flexible stamp. So far we have been rather confined to this part of the table with discussing about topographic patterns, and now you see most of the names that are written here will make sense to you. So, CFL you understand, micro molding in capillaries you understand, replica molding you understand. We have also talked about methods like SAMIM, we have talked about methods like polymer bonding lithography, and we just talked about microtransfer molding. And the last part of our discussion on soft lithography, we will now focus on how to make chemical patterns. We already understand what we mean by a chemically patterned substrate. So, essentially you have a surface like this where you have different wettability regimes, and this is achieved by the method of microcontact printing. Interestingly, this is the first soft lithography method that was developed way back in early 90s, and this relies on what is known as self assembled molecules at the surface. So, we will discuss that. So, it is a very simple method. Essentially, we use some special type of molecules, surface active molecules. Now, these molecules are primarily of alkane thiols. Okay. Some example, we will not go into the chemistry. So, these are like silanes or thiols, this class of molecules, and they have a generic structure okay. So, these are again long chain hydrocarbons, but they have the two ligands Y and X at the two ends. Okay. This out of these two ligands, Y is the one that determines. So, essentially what you have is a long chain molecule like this, and this Y end of the molecule determines the attachment to the surface. We had long time back in the initial few lectures talked about the surfactant molecules, about surfactants. So, in a way, if you have a surface and you simply immerse it, forget about microcontact printing or anything, immerse it in a solution of these surface active molecules or silanes, what is going to happen is that this Y is going to tag itself to the surface, and then the molecule will take a shape like this. So, if the surface is now fully covered with this type of a molecule, like this, what will happen? Suppose if gamma s was the original surface tension or the surface energy of the substrate, a SAM layer coated a silane layer coated surface will exhibit a completely different surface energy, and that surface energy will be the surface energy corresponding to the ligand X. So, what is SAM? SAM, this refers to a layer of self assembled monolayer. So, these molecules for all practical purpose behave as some sort of a surfactant. The moment you dip a surface which of course has the ability to bind to Y, the Y end of the molecule will come and bind to the surface, and the whole surface will get covered with these molecules. So, eventually the feature height, of course, though it looks very long, these are 1 molecular dimension. So, which is sub nanometer, maybe couple of angstroms. So, virtually there will be no change in the feature height or whatever, but effectively, so you had this bare surface and now it is coated with this layer of SAMs. Let us say the bare surface, let us say, had a surface energy of gamma s. This will for all practical purpose have a surface energy of gamma s x. Now, please do not confuse that if you coat a surface with a SAM layer, it is going to be hydrophilic or hydrophobic. It is not like that. Whether the surface energy increases or not, or what will be the generic nature of the SAM coated surface depends on the nature of X. So, if the ligand X is hydrophobic, then what is going to happen? This the whole coated surface will behave as a low energy hydrophobic surface. On the other hand, if X is hydrophilic, then after coating you can sort of get a more wettable type of a surface. So, here is the formal statement: the presence of a ligand which is reactive toward the surface ensures the attachment of the silane molecules with the substrate. The surface properties of the SAM surface, that is the SAM layer coated surface, whether it is hydrophilic or hydrophobic, depends on the nature of the head group X. And on the other hand, the binding of the SAM molecule to the surface is determined by the group Y. Some surfaces like gold or silver show excellent binding ability. So, this is important. Many times you have to coat a surface with gold or silver because they show excellent binding ability towards the silane molecules, which are alkane thiolates, alkyl siloxanes or hydroxyl terminated surfaces, etc., etc. Glass also can be used. Now, the idea is that, so after we understand this concept of self assembled monolayers, the idea of generating a chemically patterned surface essentially is to control spatially the attachment of these molecules. So, suppose you have a bare surface and instead of covering it fully with this SAM layer coated molecules, if you can somehow do something so that only parts of the surface gets covered with this molecules, then effectively what you will see different chemical patches corresponding to this. So, these are areas covered with SAM, not covered. If you dip your substrate into a SAM into a solution, of course, this is not achievable because everything will get covered with the SAM. So, this is achieved by a very simple method, and you can sort of look at this movie. So, what we have is a master pattern or a stamp, which can be a PDMS stamp, which is a PDMS stamp, and this ink is nothing but a silane solution or a solution of the surface active molecules, and this is the surface to be patterned or the bare substrate. So, what you do, you take this stamp, you dip it in the solution, it is known as the inking process. Of course, it is not possible to ink it like this, typically one dips it in the solution, and then this stamp is carried back and is simply placed on the pattern surface, on the surface to be patterned. So, what happens is the stamp which was immersed in the silane solution now contains silane molecules as the thin wetting layer around it. And when this stamp, so these are the silane of the, when this stamp is brought and placed on a bare substrate which has the desired level of reactivity with the ligand Y, and you simply place it. So, you bring it in and over the zones where the stamp and the surface are in direct contact, the silane molecules get transferred and get attached to the surface. However, over the other areas, since there is no direct contact between these areas, there is no direct contact between the stamp and the substrate. So, these molecules remain stationed on the stamp itself. So, and they cannot get transferred onto the surface. So, now when you remove the stamp, it is only over the areas which were in direct contact with the protruded areas of the stamp, the silane molecules get transferred onto the surface, and the stamp now looks something like this. So, the silane molecules which were over these areas remain attached to the stamp, but only the molecules over these zones which came in direct contact during the contact process over here, as you can see, get transferred to the surface. So, what happens? These now, if you look at a quick 3D view. So, suppose if you have a grating over this entire length of the stripe, you have these self assembled monolayers on the surface, which now act as different wettability regimes depending on the nature of the ligand X. Okay. So, this is one of the simplest methods, very easy to execute. Of course, there are critical issues. Critical issues involve, let me just draw a quick detail. So, the viscosity of the silane, the solution is extremely important, because though it is the preferential attachment that eventually guides the self assembly of these molecules onto the surface, one has to understand that if this wetting layer is too dry or the viscosity is too high, then what will happen? Even during contact, this molecule might fail to transfer from the stamp to the surface. On the other hand, if it is too wet, if it is very dilute, then not only over these areas the molecules will get transferred, but it might actually form a meniscus, and you might have a wider zone over which the molecules may transfer, which can lead to the effect of what is known as smearing for very low viscosity. So, this intrinsic viscosity is something that has to be controlled in experiments, and in many cases it is sort of achieved by drying the stamp after it has been withdrawn from the inking process or from the SAM solution. So, these are some critical experimental issues. So, this is what it is. So, this is how it looks like. It is attached to the surface, and these finally the effective wettability of the surface of a SAM layer coated thing layer is determined by the interaction or the nature of the ligand X. So, the other important aspect is we will take it up in the subsequent lectures. We will talk about it there, is what is known as the lateral force microscopy, which is important to image microcontact printed surfaces. So, this is just sort of a quick trailer I would like to give you here. While talking about atomic force microscopy, which is the next topic we are going to take up, we will talk about LFM, and we will revisit this particular image there and how it is important in in specifically imaging microcontact printed or chemically patterned surfaces. So that sort of brings us to the end of our discussion on soft lithography, soft lithographic techniques. So I will quickly revisit this classification slide again, and you now see that we understand, based on the last 6 lectures we have spent, the different aspects of different types of soft lithography methods. We now understand about this imprinting as well as the soft lithography group of techniques, and we also understand the different methods available for topographic patterning as well as for generating chemical patterns. Of course, this method is slightly unique in the sense that you are able to, not this one, microtransfer molding, you are able to generate 3D structures. Microcontact printing allows you to make chemically patterned structures, and the other ones, most of the other ones, make gives you the flexibility to make topographic features. A quick look at some of the advantages of soft lithography. So it's convenient, inexpensive, accessible to almost everyone, people most importantly who are non-experts to lithography. The basis of most of the methods is self-assembly of some sort or the other, which tends to minimize defects rather than mechanical processes or embossing like photolithography, for example, because here to a large extent you rely on the pattern replication on the forces like capillarity, van der Waals force, self-assembly, etc., etc. Many of the soft lithographic processes are additive and therefore minimize the waste of material. You really do not go in for processings like etching, you do not require that, which essentially is nothing but wastage of material. So it can be, the methods can be readily adapted for rapid prototyping. Isotropic mechanical deformation of PDMS mold provides route for complex patterns. There is no diffraction limit. This is extremely important. So photolithography is significantly limited by the diffraction of the wavelength of light source you are using, and 30 nanometer, not even 30 nanometer features as low as 10 nanometers has been achieved way back in 2005 itself. Use of a flexible stamp allows you to pattern films coated on non-planar surfaces. So lenses, optical fibers, capillaries, etc. can be used as substrates. Generation and replication of 3-dimensional topographies are possible. Microtransfer molding we have already talked. Optical transparency gives you the allows through mask registration and processing in some methods like we have talked about this SFIL. Good control over surface chemistry, which is extremely useful for interfacial engineering. A broad range of materials can be patterned: functional polymers, sol gel, colloidal material, suspension, solution, precursor to carbon material, glasses, ceramics, etc. It's not limited to only one set of materials like photoresist, which is the case with photolithography. Applicable to manufacturing, so indistinguishable copies can be made at low cost and patterning over large area can be achieved. Some practical limitations: the patterns in the stamp or mold may distort due to deformation, issues like pairing, sagging, swelling, shrinking, etc. We have already talked about the fact that soft lithography is to a large extent limited by the availability of the appropriate type of a stamp, which is of course a limitation one has to understand. Efforts are being made to make it compatible with current IC processing and technologies, so that this can be extended. The soft lithography group of methods can be extended to the microelectronic paradigm, microelectronic industry. Defect levels of course higher than photolithography, and therefore which makes it hinders its utility for the microelectronic industry. Microcontact printing, there are some material restriction for some of the methods. For example, microcontact printing works well with a limited range of surfaces like gold or silver coated surfaces, as we already talked, because the surface has to offer good binding with the Y ligand. Mimic is slow because it's a capillary driven process and it doesn't work for long lengths. Replica molding, microtransfer molding, and SAMIM leave a thin layer of polymer, or the remnant layer, as we have already highlighted, so which has to be removed by reactive ion etching or things like that. But still, soft lithography is a very exciting area, very advanced area of research, where a lot of research is still going on in different aspects, materials, beyond the master patterning and things like that. And it is sort of a it can be implemented without significant infrastructure, which is absolutely mandatory in photolithography. So I'd strongly encourage you to look into, do some literature review on soft lithography with keywords like soft lithography or the names of the technique you have understood, and sort of augment whatever you have learned in this course on soft lithography. Thank you.